the test we discussed so far are applied to one sample only. Even in the special situation, matched pair T test, those two samples are dependent, and we are interested only in the difference between the two samples. So what we did is we subtract the two sets of data from each other, and we construct a new variable, and we convert the two samples into a one sample problem. Those two samples are dependent. Sometimes we need to solve problems with independent samples. Independent samples are where subject in one samples are completely unrelated to subject in the other sample. So we often compare two treatments used in independent samples. So here is an illustration. We have one sample, sample 1, here, and we have a sample 1 here, and we have another sample, sample 2. And we know sample 1 and sample 2 will be different. Now the question is this sample 2 from a completely different population than sample 1, which means sample 1 is from population 1, sample 2 is from population 2. Or this different sample 2 comes from the same population as the sample 1. The difference between sample 1 and sample 2 is just because of the random variation. To answer this question, this one, the two samples are from different populations, or the two samples are from the same population, we are going to use a two-sample z-test. Here we have two independent simple random samples, possibly coming from two distinct populations. And the first population satisfies a distribution, the mean equals mu1, the standard deviation is known, which is sigma 1. And the second population is satisfied with the mean equals mu2, and the sigma 2 is known as the standard deviation. And the two samples are from these two possibly distinct populations. And we know the mean of the sample 1 and the mean of the sample 2. We are going to use x1 bar to estimate the unknown mu1. And we use the x2 bar to estimate the unknown mu2. But we know sigma 1 and we know sigma 2. Because we know the standard deviation of the two populations, so this is a t-test. But we have two samples, so that's why it's called two-sample t-test. Here, we need to, if both populations are normal, then the sampling distribution x1 bar minus x2 bar, the difference between the two samples, is also normal. We know this from the previous chapters. And the standard deviation of the difference between these two samples is sigma 1 squared over n1 plus sigma 2 squared over sigma 2 over n2. Then take the square root. So this is the sigma. The next step is we need to standardize the normal distribution of the difference. And we construct a z-score with, because as we said, we are interested in the difference. So x1, so this one is as x. X equals x1 bar minus x2 bar. Okay? And so this is x bar, and mu1 minus mu2 is the difference between the two unknown mean of the population. So this is the mu. And this one here is the standard deviation. Recall that in one sample z-test, this standard deviation here is equal to sigma and over square root of n. But here, because we have two independent samples, the variation needs to be added up together. So the first variation equals n1 sigma 1 squared over n1. So that's the first one. Then the second one is sigma 2 squared over n2. These two variances add up together equals the total variance of the difference. Then we take the square root. This gives us the standard deviation of the difference of the two samples. So this is the sigma. The next step is to state the hypothesis. The H0 is because we want to test if these two samples are from the same population. So the H0 is mu1 equals mu2. We want to test this. So that means the difference between these two means will be equal to 0. So that's the first one. And the alternative hypothesis will be one-sided or two-sided. Depends on greater than or less than or not equal to. In the last slide, we discussed the two independent sample normal distribution or z-test, where we know sigma 1 and sigma 2 for the both populations. How about if we don't know sigma 1 and sigma 2? Sigma 1 here and sigma 2, we don't know both. That means we are going to use a t-test. To compare the means, both populations should be normally distributed. However, in practice, it's enough that the two distributions have similar shapes and that the sample data contains no strong outliers. Even they are not normal distributions, we can still use this procedure. In two sample z-test, we use sigma equals sigma 1 squared over n1 plus sigma 2 squared over n2, then take the square root. This is called the standard deviation. But in two sample t-test, we don't know sigma 1, we don't know sigma 2. Instead, we are going to use the standard deviation of the two samples, S1 and S2, to approximate the population standard deviation. So that gives us the standard error, so similar to the standard deviation, which equals square root here, and replace sigma 1 and sigma 2 with S1 and S2. So this is for two sample t-test. When we study t-test, we need to consider another parameter called degree of freedom. And because we have two samples here, so we have N1 and we have N2. So the degree of freedom for N1 equals N1 minus 1. The degree of freedom for the second sample is N2 minus 1. It is not necessary that N1 equals N2. Sometimes N1 and N2 will not be equal. So which one is the degree of freedom? And to be safe, we choose the smaller one of these two as the degree of freedom of these two independent sample t distribution. So we are going to use the smaller one of these two degree of freedom. As in the two sample z-test, we're going to, next one is to state the hypothesis. Again, because we want to compare if these two samples are from the same population. So H0 will be mu1 equals mu2, which means mu1 minus mu2 equal to 0. With either one-sided or two-sided HA. The t score, or the t value, is calculated from x bar minus the mu, then divided by the standard deviation of the called standard error, which is before, for one sample, it is sigma. There's no sigma. Okay, there's s, then divided by the square root of n, so that is before. Now we need to use n1 squared and plus over n1 and plus s2 squared over n2, then take the square root. So that is SE. So this part is here. Because H0 is mu1 equals mu2, or equivalently mu1 minus mu2 equal to 0. So this mu1, mu2 will be equal to 0, because that is here. So that means on the top we have only x1 bar minus x2 bar. And on the bottom, that is the standard error, which is this or this one. And don't forget the degree of freedom equals the small of n1 minus 1 and n2 minus 1. Okay, so up to this point, we have all the knowledge to calculate two sample z-test and two sample t-test. The difference between these two is one, in the z-test, we know the standard deviations of the two populations. And for the t-test, we don't know the standard deviation of the populations. Instead, we are going to use the standard deviation of the samples to approximate them. So we are going to calculate the z-score and the t-value respectively. Once we calculate this, we can solve the problem. So next one, we are going to use one example to show how to do this. This is called a two-sample t-significant test. Two-sample z-test is easier than this because we don't need to consider the degree of freedom. So here we want to know whether parental smoking decreases children's lung capacity as measured by the forced vital capacity FVC test. Is the mean FVC lower in the population of children exposed to parental smoking? That is the question we want to test. Here we are given two sets of data, and we already get the result solved. For example, for the first sample, the smoking parents, and the mean of the sample equals 75.5, and the standard deviation equals 9.3, and the size of the first sample equals 30. In the second random sample, which is non-smoking parents, and the mean of the sample equals 88.2, and the standard deviation of the sample equals 15.1, and the sample size also equals 30. So we calculated the mean of the two samples, the standard deviation of the two samples, and we also know the sizes of the two samples. The next one is to state the hypothesis. H0 is because we want to test if there's any difference. So the mu, the smoke population, equals the mu for non-smoking population. That means there's no difference. That means mu smoke minus mu non-smoke equal to 0. And the alternative hypothesis is the mean FVC will be lower in the smoking parents. So that means the mu smoking less than the mu non-smoking. That converted into mu non-smoking minus mu smoking minus mu non-smoking will be less than 0, because this is the lower, so less than 0. So this is a one-sided test. The next one, we know the difference between these two samples satisfy a t-test because we don't know the standard deviations of the two populations. So this is a t-test. the t-test satisfy 0, and the standard error equals s squared over n smoke plus s squared non-smoke over n non-smoke, then take the square root. And the degree freedom equal to 29. Because here, df equals 29, and this one, df equals 29. The smaller one is still 29. The next step is to calculate the t statistic. The t statistic equals x smoke minus x bar smoke minus x bar non-smoke, then minus 0. Minus 0 here, this 0 is from here, this 0. But because minus 0, so we just ignore this. Then divided by the standard error is this. So we plug into numbers. This one here equals 75.5, and this one, x bar non-smoking equals 88.2, and this f squared equals 90.3, 9.3, and this one equals 30, this one equals 15.1, and this one equals 30, and take the square root. This number gives us negative 3.9. As discussed in the normal distribution, where we use a t statistic, we only care about the absolute value. So we don't need to care about the negative sign. So this one means t equals 3.9. Right? The next is to calculate, to look up table D. Table D here, and degree of freedom. Okay, this one is 29. Degree of freedom 29. We are interested in this line. Then we find the t value equals somewhere is 3.9, and we found that it is larger than 3.6.5. Our t value is here, but this one is called 3.6, and this corresponding to a value, a probability that 0.0005. This is for one-sided test. So our p value will be less than, the p value will be less than this. So this definitely less than 5%. So that means this is a significant difference. So our conclusion will be we reject H0. From this example, we can see there are almost no difference between how to calculate the two-sample z-test or how to calculate the two-sample t-test compared to one samples. The only difference is we need to construct the difference, and we need to use the difference, and when we calculate the standard deviations, this is different than one sample. So this, we need to keep this in mind. Alright, we finished the significant test. Then recall that we can also discuss the confidence interval. So same thing applied for two sample, we can calculate the confidence interval. Remember in one sample, the confidence interval will be equal to means. Confidence interval means the mu equals x bar plus minus, and for z-test that will be z star, then times the standard deviation divided by n, and for this is for z-test. For t-test, this one will be x bar plus minus the t star, then times s, because we don't know the standard deviation of the population. So instead we use the standard deviation of the sample. So f, then take the square root of n. So recall, we know that. This one is very similar. So this part here and this part here is called the margin of error. For two samples, so see the margin of error will be t star here, then multiply by the standard error, which is for 2 samples will be S1 squared over N1 plus S2 squared over N2. And before, for 1 sample, we only have this one. So that's the only difference compared to what we discussed before. So I don't think we have any problems. Another difference is the degree of freedom we need to take care of 2. We need to choose the smaller one, because one is N1 minus 1, another one is N2 minus 1. Most probably N1 will not be equal to N2, so we take the smaller one for safety. All other concepts, the T stars, okay, so confidence level C are the same. Before we use an example to show how to calculate the 2 sample T confidence intervals, we want to state some common mistake. When compare 2 samples, a common mistake is first one, we have 2 samples here. One is this, another one is this. What we can do is, for the first one, we calculate the mean of the population. So this is population 1, this is population 2. And we assume we calculate approximate the mu1 is x1 bar plus minus the T star or Z star, right? Because the standard error. So from here, then plus and minus this standard SEM. Now we can compare this value x2 bar to compare if this one is within this range or not. If this one is within this range, then we say, okay, this is from these 2 samples are from the same population. If this one is outside this range, then we say these 2 samples are from different populations. And this is, as we said, this is wrong. We cannot use this method to do this. The reason is, in this method, we only consider the variability of the first population or the first sample. We do not consider the variability of the second. Because when we calculate this, we use S over square root of N, then times T star, or, let me write here, and in this one, the SEM is equal to T star times S over square root of N, 1, or equals the Z star times sigma over N1 here. But we do not consider the variation of the second population or the second sample. So this method is too simplified to solve this. Our 2 sample problem is much more complex than this simple method. So this simple method is not correct. We cannot use this method. Instead, we need to use this standard error equals S1 squared over N1 plus S2 squared over N2, then take the square root. We need to consider the variations from both populations, from both samples. So keep in mind, we cannot use this method to compare 2 samples. The next one, we are going to use an example to show how to calculate the 2 sample T confidence interval. Before we do this, you can imagine this should not be that difficult because we already know how to calculate the 1 sample T confidence interval. The question is, can directed reading activities in the classroom help improve reading ability? A class of 21 third grader, 21 third grader, that means N1, right, equals 21. Participates in these activities for 8 weeks, while a control classroom of 23, this is N2, equals 23. So you can see N1 and N2 are different. Follow the same curriculum without activity. So this is the control sample. After 8 weeks, all children take a reading test. And we have the test scores. This is a treatment group, this is a control group. Here we have 21 data, this one we have 23 data. What we want is what is the 95% confidence interval. This is what we want. We want this one. For the difference, because we want to see if this activity will give us a difference. So we calculate the difference between these two samples. For the first sample, we are given 21 numbers, and we calculate, we know A1 equals 21. The mean of this number here equals 51.48, and the standard deviation of the first here equals 11.01. And for the control group, the size equals 23, the mean equals 41.52, and the standard deviation equals 17.50. So we have all the numbers we need to calculate the confidence interval. In addition to, we know the C equals 95%. First one, we need to consider the degree of freedom. The degree of freedom for here, df1 equals 21 minus 1 equals 20. And df2 equals 23 minus 1 equals 22. So we are going to use the smaller one. That means df equals 20. And T star, remember in the table here, this is confidence level C, and for 95%, so 95% is here. Correspondingly, for degree of freedom, this is df here. df equals 20, and this here is C, and this gives us the T star. The cross section gives us the T star, which equals 2.086. So T star equals 2.086. And S1 is given here, and S2 is given here, and 1 and 2 both are given, so that square root gives us 4.31. Then multiply by T star, this gives us 8.99. And that is called the standard error. So the confidence interval, if we still recall for one sample, the confidence interval equals x bar plus minus the standard error. So that is for one sample. Now we have two samples, so that will be the difference. So this one will be replaced with x1 bar minus x2 bar. And this m is calculated from here equals 8.99. So the confidence interval for mu1 minus mu2 will be between x1 minus x2, x1 bar minus x2 bar, so x1 is this, x2, so this one will be equal to 51.48, and this one here will be equals 41.52. These two subtract each other give us 9.96. So this minus this equals this, and this 8.9 is from here. And this minus this gives us 1.0, and this plus this gives us 18.9. So the confidence interval is 1.0 to 18.9. So the conclusion is we can see with 95% confidence that the difference of the score will be between 1 to 18.9. Okay, next one we are going to discuss how good are these two sample t-test on the robustness. Two sample t procedures are more robust than the one sample t procedure. They are the most robust when both sample sizes are equal. If we have an example, the first example, both sides equals 30, and in the second sample, the first size equals 21, the second size equals 23. Both sample sizes are not equal, but they are most robust if the two sample sizes are equal, and both sample distributions are similar. But even when we deviate from this two conditions, two-sample test tend to remain quite robust. When planning a two-sample study, if we can, you choose equal sample size. As a guideline, a combined sample size N1 plus N2 of 40 or more will allow us to work with even the most skewed distributions. Okay, so this is the end of this topic.